brief introduction showing how phase retrieval can be performed with gradient descent, and we will later extend this to phase design. To do this, we will make use of some of the automatic differentiation softwares that are available now. And basically, we'll use these to automatically calculate the gradients we need for our gradient descent. For phase retrieval, you can imagine that what we start with is some point spread function, PSF, at the detector. And we're going to work back through our optical system to determine what the original phase was that produced that PSF. Gradient descent will work for this problem as long as you can simulate your optical system with a set of differentiable equations, and lucky for us, most of the time you can. Let's run through a quick example. So here is a target PSF that I have, and I want to work out what the original phase is. I'm basically going to start with some noise and use that to estimate a PSF. Now I will compare the reconstructed PSF with the true PSF, and my objective is to minimize the difference. Using gradient descent, I can then propagate this information back to the pupil so I know how to change the phase values to reduce my error. You can also perform phase retrieval even if the PSF you're working with is saturated. Essentially, before you calculate your error, you also saturate your reconstructed PSF. You can also impose other arbitrary constraints. Here is an example where we performed phase retrieval on this weird looking pattern called the quantum monodromy pattern. So right now, this is just a straight phase retrieval. If we wanted to add a constraint, all we need to do is add a term to the objective function. So in this case, for whatever reason, we've decided to impose a 4-phase coloring on the pupil. And so all we need to do is add in a term that penalizes phase values deviating from our 4 allowed phases. Now we're going to borrow all of the machinery we just used for phase retrieval and apply it to phase design. Essentially, the key thing that you need to do is switch out the objective function. So here you can see that instead of reducing error with some arbitrary PSF, we can perform phase design where we do a naive optimization of an APP coronagraph by having a metric that says get rid of all the starlight in the dark annulus while keep as much of the starlight in the central peak as possible. Another really cool application is in diffractive pupil design. So for example, the upcoming Tolman Space mission. So this is an ambitious mission aiming to detect exoplanets using high precision astrometry between Alpha Centauri A and B. And it does this by measuring overlap between PSF fringes. The final design requirements for the Tolman pupil are subject to ongoing review, but essentially you want a flat top disk with a lot of peaks. The pupil must be binary with equal areas of 0 and pi phase to induce a null at the origin of the PSF, and regions in the pupil must be reasonably sized for fabrication purposes. We did have to come up with a tricky objective function to incorporate all of these constraints, but we basically just used it, ran gradient descent with a number of different initializations, and here are some of those really cool results. Hopefully you can see that this method of applying gradient descent to phase retrieval and phase design is really versatile and easy to implement, and you can simply plug and play gradient descent for any of these kinds of problems.
Hi everyone, I'm Aman Chokshi, a PhD student at the University of Melbourne. In this talk, I'm going to be telling you how beam models of low-frequency radio interferometers, such as the Murchison Wide Field Array, impact rotation measure synthesis and studies of radio polarized sources. Radio interferometers are inherently fully polarized instruments, making images in all Stokes parameters, I, Q, U, and V. The IgM and ISM plasma acts as a birefringent medium with magnetic fields in this plasma rotating the plane of polarization of any linearly polarized radio light. Rotation measure synthesis is a powerful technique which is achieved with the Fourier transform along the polarization angle to determine what's known as a Faraday dispersion function. The peaks of this Faraday dispersion function are identified with distinct Rm values, each of which corresponds to a different component of magnetic field along the line of sight. In this work, we simulate a simple interferometer and introduce phase errors to the beam models. What we observe is with phase errors of less than 2 degrees, leading to a significant depolarization of our radio source. And as we exceed 3 degrees of phase errors, we observe a mirroring of our rotation measure value, which can be interpreted as a reversal of the magnetic field, which is false and only due to the imperfect beam model. In future work, these simulations will be extended to a much more real interferometer comparable to the MWA, and we'll also be studying the effects of beam models and on epoch of reionization signs. Thank you for listening, and get in touch if you're interested in such work.
Hi, my name is Anna, and today I'm going to talk to you about trihybrid line lists, what they are, why we need them, and use CN as an example throughout. Well, what is a line list to begin with? A line list essentially describes a molecule's spectroscopic nature. It is a collection of its energy levels, transition line positions, and transition intensities of that molecule. It's often used to predict absorption spectra or as input to sophisticated models of gaseous environments. The applications for line lists are wide and varied, starting from the likes of fundamental physics and going through a myriad of different applications where you might need the spectroscopy of a small molecule. My personal use is for fundamental physics, where I use it to calculate sensitivities of transitions of small molecules to a variation in the proton to electron mass ratio, but I won't be going through much of that, any of that today. What I will be going through is how these line lists come to be and how we might want to optimize these line lists to get the most accurate data. There are three main pathways for this line list data production, and they each have their own advantages and disadvantages. Often you'll see a combination of two different approaches, but very rarely are they all three of them combined. So these three approaches can be broken down into a variational approach, often using DUO for diatomic molecules, which is based on solving the Schrödinger equation using potential energy curves. It is also very complete in its nature. We have an experimental approach using MARVEL, where experimental transitions are able to produce experimental energy levels. Doesn't give very good information about our intensities, but and is also reliant on how much experimental data is done. And we have our perturbative methodology, which is using experimental data to extract band constants and use model Hamiltonians to derive our energy levels. Very good at interpolating information, but isn't so good at giving you the complete picture. Putting all three of these together, though, we can create a trihybrid line list. What we have to think about with our trihybrid approach is which of the two theoretical approaches, perturbative and variational, will have better energy levels. What we can look at is the residual between our variational method and our experimental method, and our perturbative method and our experimental method, to see which has a lower uncertainty. And we can see from this plot for CN that our perturbative methodology gives us a lower uncertainty for our energy levels. So here we prioritize our perturbative energy levels over our variational energy levels. Putting all our energy levels together with our variational transition data, we have created over 2 million transitions for CN between 0 and 60,000 wave numbers. And we can see here with our cumulative distribution of across intensity that 90% of our strong transitions have experimentally derived energy levels. We can use this to validate and explore where we might need more experimental data. For CN, below 30,000 wave numbers, our line list matches the experimental data very well. We see that above 30,000 to 40,000 wave numbers, we are tending to rely more on our theoretical data than our any experimental data available. This can be used to validate other line lists and identify where more experimental data is needed. These are the references that I've used throughout my talk, and I just want to say a big thank you to everyone at UNSW and NSAID that has helped me with this along the way. Thanks.
Hello, my name is Daniele D'Antonio. I am a PhD student at University of Technology, Sydney, and now I'm going to talk about variable AGN. For this work, I used catalogs listing AGN, and I searched for their counterparts in two radio surveys, which are RACS and the VAST Phase 1 pilot survey. And in these two radio surveys, I found over 2,000 AGN. Here in this plot, we can see modulation index percentage versus chi-squared. The black points are non-variable AGN, and the red points are variable AGN. I found that 33 objects are variable AGN, and this means that 1.39% of the sample is variable. The radio variability is due to scintillation. We know this because we estimated the brightness temperature values for all the variable AGN. In this histogram, we have number of variables versus logarithm of brightness temperature. And we see that all the values are above this number, 10 to the power of 12 Kelvin, which is the Compton catastrophe limit. We cannot have intrinsic variability with values above these limits. And we also consider the possibility to have Doppler boosting effects. So we divided the brightness temperature values by a Doppler factor, but the values are still above these limits. Another result is that looks like blazars are more variable than other classes of AGN. In my AGN sample, I have different kind of AGN. I have Seyfert galaxies, liners, quasi-stellar objects, and blazars. So in this plot, we can see chi-squared versus flux density. The black points are blazars. The red points are mainly all the classes of AGN I mentioned before. And we can see that the blazars have larger chi-squared, and the physical interpretation is blazars are more variable than the other AGN. Another thing we have done is to use a scintillation model, which gives prediction of the modulation index values for objects varying because of scintillation. And what we have done is to compare the modulation index values that we observed with the ones predicted by this scintillation model. In this plot, we have modulation index percentage versus time scale for all the variable AGN. And the red points are the observed data, so the observed modulation index values. And the black points are the modeled predictions. And we can see there is a gap. We think this gap might be due to electron density variations in the galaxy.
Hi, my name is Eduardo Schiapucci. I'm here to talk about cosmological constraint forecasts with pairwise KSE that I've been working on with the SPT and DES collaboration in the past year. And we're hoping to do this on real data very soon. But for starting with the forecast, let's start with explaining what is the pairwise KSE. So the Sondyaev-Seldovich effect is simply the change in photon energy of the photons that come from the cosmic microwave background due to clusters that are in the way from the cosmic microwave background to us. These clusters tend to move towards or away from us, and this gives a boost or a decrease in the energy of these photons. Now, because clusters tend to move towards each other because of gravity, then this creates a pairwise signal in the CMB that we can measure, and this signal is dependent on cosmology and astrophysics, but we're more interested in the cosmological part, especially in the linear growth factor, which constrains general relativity and can give way to modifications of gravity. Now, to do this forecast, we take some Sondyaev-Seldovich simulations, and we simply apply the noise levels of what our third generation SPT cameras are gonna receive, which is the current cameras. And also we have to add redshift uncertainties due to the fact that the DES cluster catalog obtains these uncertainties from photometric redshifts, and they gives around a 0.01 uncertainty on the redshift of the clusters. Now we can reproduce older pairwise signals that have been done in the first generation SPT as well, which gives us confidence that what we're doing is correct. And we see that the improve with current SPT and DES catalogs and maps is around a 20% improvement compared to this signal before. And we also check actually that the current limiting factor is the photometric redshift errors. So if we in the future expect a future like spectroscopic surveys like Foremost or similars, the simply the fact that we don't have these redshift errors gives an almost 100% improvement on the signal and almost triple the significance on the cosmology that we can achieve. Thank you.
Hello there. My name is Gavin Rao. I'm going to give you a brief overview of the new group for astroparticle physics, or GAP. This is the first joint group to be run under the auspices of both the ASA and the AIP. I'll be speaking to you today on behalf of the GAP Formation Committee, Harry Bignell, Mark Doldig, Clancy James, and Yvonne Wong. We've been working together now for just over a year on the formation of the GAP, and that has been developed with a large number of community support. So the purpose of the GAP is to close the gap, so to speak, between astronomy and particle physics in Australia. This is a field known as astroparticle physics. These various images show you just the wide variety of science topics that astroparticle physics covers, including accelerators of extreme particles, cosmic rays, and so forth, which then lead to all different types of photon and particle messages, from radio all the way up to gamma rays, and particles such as neutrinos and cosmic rays directly. We also have topics such as beyond standard model physics, such as different theories of dark matter, and how we can probe those different theories using astronomical observations. There's also the particle physics of the early universe, often known as particle cosmology, and how the particle physics of the universe has influenced its evolution. And so the purpose of the GAP, or this group for astroparticle physics, is to support the professional development of the astroparticle physics community in Australia. It will promote the discipline of astroparticle physics to the community. It will help to link the national and international astroparticle communities to activities locally and overseas. It will advise the AIP and the ASA on various matters relating to astroparticle physics engagement strategies. And finally, last but not least, it will also help to support the research and education in this field and the engagement with various facilities that carry out astroparticle physics. So one of the key points of the message today is to announce that there will be a new GAP steering committee, the long-term committee that will run the GAP. The GAP committee will comprise of 2 co-chairs, one from the AIP and one from the ASA. There will eventually be immediate past chairs, of course. The committee will include 5 regular members, which will include the secretary and the treasurer. There'll be 2 student members, and there'll be 2 non-voting members, one each from the AIP executive and one from the ASA council. And so we will soon issue a call for nominations across various email lists. And I should also point out that the GAP, or the Group for Astroparticle Physics, has its own dedicated email list here, you can see. And if you wish to sign up, please follow this web address. Okay, thank you very much.
Hi everyone, I'm Himanshi, a PhD student at Monash University, and today I will be presenting a few recent results on the kinematics of spiral arms in the HD 142-527 system. To start off with a brief summary on the source. So HD 142-527 is an intermediate mass pre-main sequence star located approximately 150 parsecs away with a low stellar mass companion in close orbit. The second binary disk surrounding this pair consists of a gas pressure dust trap that gives the dust component of the disk a unique horseshoe-like morphology, which is seen in millimeter to sub-millimeter wavelength thermal continuum emission that primarily stems from dust grains. So looking at gas emission at millimeter wavelength, on the other hand, reveals several large-scale spiral arm structures that extend to distances of up to 650 AU from disk center. In a recent study by our team, we used ALMA observations at 0.3 arcsecond spatial resolution and found that the same spiral arms but traced at 2 different disk altitudes using 12 and 13 CO gas tracers were radially offset. So in protoplanetary disks, temperature is expected to increase from the midplane up to the surface layers. Due to the varying optical depths between 12 and 13 CO isotopologues, emission from 12 CO is tracing gas much higher up in the hotter disk layers than 13 CO, which is found further down and closer to the cooler midplane. So being gas density waves, spirals propagate at sound speed, where the sound speed is dependent on the local temperature of the medium the wave is propagating through. Therefore, the presence of a non-zero vertical temperature gradient implied that the speed at which the spirals were propagating outwards varied between the two traces. So we made the conclusion that the radial offset we were seeing was due to the spiral arms surfing on this vertical temperature gradient, whereby the 12 CO spirals had propagated out faster and thus further, whilst the 13 CO counterpart spirals were trailing behind. Furthermore, these spirals were also found to not be in Keplerian rotation. When viewed through channel maps, the spirals are seen to extend into regions of the map that corresponds to either higher or lower velocities than the expected Keplerian velocity, thus deviating away from the bounds of expected Keplerian rotation. Focusing on the innermost spirals in particular, at extremely high blue shifted velocities, emission is seen to extend into a region of the map that would normally be occupied by emission at lower blue shifted velocities. This therefore makes the spiral super Keplerian in this region of the map. Conversely, this switches over in the redshifted region of the map, where the same spiral transitions to be sub-Keplerian. The perceived velocities here are likely a combination of both azimuthal and vertical motion in the disk, where a vertically ascending spiral would replicate the transition from super to sub-Keplerian rotation, because the Doppler shift in the red-shifted regions would be attenuated, whereas in the blue-shifted regions, the Doppler shift would increase. Thank you for listening, and for full details, please refer to our paper cited below. Thank you.
Hello, everyone, and thank you for taking the time to listen to my talk today. So my name is Ian Hendrickson, and today I'm speaking on behalf of the MIST collaboration to talk to you about the development of an antenna beam model interpolation package for Python. So first, a brief background about the MIST experiment, which stands for the mapper, the IGM spin temperature. We're a new cosmology experiment, and we're aiming to measure the global redshifted 21 centimeter signal to study the evolution of neutral hydrogen in the IGM during the dark ages, cosmic dawn, and epoch of reionization. So MIST is an experiment that requires a lot of electromagnetic simulations to characterize its antenna beam gain with very high accuracy. The problem with this is that full EM simulations can potentially take a long time to calculate. So this presentation is going to detail the development of a Python package that uses interpolation instead of simulation in order to significantly reduce the time it takes to produce new beam models. So I'll briefly go over the interpolation process, but I invite you to go to the MIST website in case you're interested in further details. Essentially what the interpolation process entails, which is detailed in figure 1, beginning with a couple of simulated antenna beam cubes, which is just a 3D visualization of the points of a simulated beam model. And each one of these simulated beam cubes is associated with a different set of physical parameters. So if we hop over to figure 2, this is the baseline antenna design for MIST. It's a blade dipole, and it's characterized by some physical parameters as well as the properties of the soil beneath the antenna. And essentially what we do is we're going to take if we go to a certain frequency, azimuth, and elevation point in the simulated antenna beam cubes, we can fill these into an intermediate antenna parameter cube at the physical parameters associated with each one of them. And then we can make a linear or a higher order polynomial interpolation in order to determine what the gain would be for an antenna having the physical parameters of the white cube. And we can loop this process over until we've filled up an entirely new interpolated antenna beam cube. So to determine the accuracy of these interpolations, we've created 27 simulated antenna beam cubes in FICO, as well as 3 additional ones with which we can compare interpolated antenna beam cubes. So the results of this are detailed in table 1, with the parameter sets and whichever parameters, the physical parameters associated with each of those. And we're using the root mean square percentage to quantify the agreement between simulations and interpolations. So what we find is that the interpolations are highly accurate in comparison with their simulated, the analytical simulated beam models. And the runtime is very, very fast. It's below a second in each case. And then if we can bounce over to figure 3, basically what this is showing is the fractional deviations between simulation and interpolation for parameter set P1. So for all frequency and all elevation and for azimuth equals 0 degrees. And there's small fractional deviations and smooth behavior. So both of the results from table 1 and figure 3 demonstrate that the package can both interpolate new beam models accurately and in under a fraction of a second, which is very important. And future work is going to involve further comparisons between simulations and interpolations, as well as seamlessly incorporating the package into the MIST pipeline. And finally, I'd just like to briefly thank Professor John Sievers, whose code helped to dramatically increase the speed of the interpolations. And of course, I'd like to thank my supervisors, Professor Chang and Dr. Monsalve, as well as the rest of the MIST team for their guidance and support. And if you'd like to email me any correspondence, you can find my email below, as well as you can go to the MIST webpage. Thank you very much.
Hey everyone, my name is Jay Clark. I'm a PhD candidate based at the University of Southern Queensland. And before I get started, I'd like to acknowledge the traditional owners, the land on which I'm coming from today, the Gaia Bolanjawa people, and like to pay respects to their elders, both past, present, and emerging. Now, I'm here today to talk about my poster here at the ASA, How do Stellar Surveys Improve the Properties of Planetary Systems? So if you've seen this before, awesome. We're going to learn more about the science behind this poster. And if you haven't, awesome. Check it out after this video. So we have uncovered well over 4,000 planets orbiting stars in the night sky, and well over 6,600 planets waiting to be confirmed by ground-based observations around the world. And so we can look at these planetary systems and be able to see the transit depth and the radial velocity measurements to be able to understand the size and mass of these planets, but that is all based upon the stellar parameters. The effective temperature, the log G, the mass and radius of those stars is crucial to then better understanding the mass, radius, density, composition, and we can go further on into characterizing these worlds. What type of atmosphere would they have? What type of geology would it have? Then better characterize what worlds are really Earth-like. So that's what I've been trying to do as a part of my PhD research. And this is an amazing plot showcasing the overlap between the Galar's latest release, Galar DR3, and the test sectors, the Transiting Exoplanet Survey satellite, and where it's been observing. And there's a huge, beautiful overlap here. So then why not utilize the information from both TESS and Galar? The question which I'm trying to answer as a part of my PhD project is, what can we learn about current exoplanetary systems orbiting around Galar stars? And so what I've been able to use is I've been able to utilize Galar's latest data release and use the effective temperature, log G, the overall metallicity, and as well as Gaia's parallax and magnitude values, 2 Max's magnitudes, to then use in an isochrone model to determine the mass, radius, luminosity, age, level zones of these stars, which then affect and then flow on into the planetary parameters. So what have we been able to learn? Well, I've been able to better characterize super Earths, and in particular these short period super Earths, down to a precision much better than has been previously documented, using not only these new stellar parameters, but also the NASA's Exoplanet Archive, and be able to use a weighted mean approach to better estimate the planetary properties, being your radial velocity and your transit depth measurement. So combining all of that together, for example, CORAT 7b, I've been able to better characterize that well down to a precision of 3% for its radius and down to less than 8% for its mass. And so we are now at a better stage now to then characterize these worlds, what they're made out of, and continue further on with its habitability. Now, with Core 7b with a surface temperature of 2500 Kelvin, probably not the case. We're probably never going to find life there. But what we've also been able to discover is that it seems like ultra hot planets, regardless of whether it's a hot Jupiter or a hot Neptune or a hot terrestrial world, tend to favor iron-rich stars and also favor younger stars as well. And so here there's older stars, and down here are younger stars. And so we're seeing that the formation mechanisms for hot Jupiters and hot Neptunes and hot terrestrial worlds might be very similar, and that this process might happen as there's more material around, and less likely to happen where there's less material during younger population stars. And also what I've been able to do as part of my research is be able to determine, well, can we actually follow up these planets from the ground and be able to work out a mass measurement? And it turns out it's going to be incredibly difficult for these stars, for these planets over here. But it's going to be pretty easy to then follow up for these planets over here. So over here, going to be up here, almost impossible, but probably doable for here. So that means that it's probably going to be easier to confirm hot Jupiters and hot Jupiters around glass stars than it is to try and determine your smaller ones here. So that's all I have. Here's my summary for my talk. And if you want to learn more, check out my poster. Thank you so much for your time.
Hello everyone. Since the 2019 ASA, Data Central, as part of the ODC, has been working on new services, as well as updates to our existing services, to make astronomy research more efficient. These include our new virtual observatory services, SIA and SSA, which let you find and download images and spectra respectively. We've put numerous examples online to help you get started, and show how to combine our services with those from SkyMapper and Castor. We've added new services for research teams, such as private data releases, which the SAMI team used to provide their reviewer with preliminary access to their third data release. We've also got some really powerful services in the pipeline, one of which is our data aggregation service. Sparked by a discussion with the Craft team, our data aggregation service will allow users to rapidly query both Australian and overseas archives and services, all in one place, without having to mess around with the frustrating differences between them. We've also been working on adding automatic data reduction of AET data, starting with the 2D FDR pipeline with AOMEGA. We hope to expand this to other AET instruments and to other telescopes, avoiding the need to get pipelines running locally. Click on the links in the PDF to find out more about what we're doing, and contact us via our website if you have questions, or talk to us here at ASA.
Hi there, my name's Jennifer Hardwick and I am a second year PhD student here at ICRA UWA, and this poster here is showing some work in a recently submitted paper of mine. So in this work we use single dish H1 observations to determine the specific angular momentum for 564 nearby galaxies. These are from the XGAS sample, which stands for the Extended Galax Arecibo SDSS Survey, or XGAS, which is selected to be a relatively flat stellar mass distribution between 10 to the 9 and 10 to the 11.5. And what this means is that we have a large fraction of high mass early type galaxies, more so than you'd expect from a volume limited sample. We assume a constant velocity for all radii, which we take from the H1 width of the galaxies in this XGAS sample, and we assume a constant velocity profile when we calculate specific angular momentum for each of our galaxies. So shown here in the center is the stellar-specific angular momentum stellar mass relation, and in the thin black line there I am showing the best fit to that relation, which we calculated using a Bayesian fitting tool called HyperFit. So the slope we determined for this relation was 0.47, which is actually the shallowest slope in the literature to date. And what we show in this work is that this slope is highly dependent on the mix of galaxy types that you have in your sample. And because our sample has a higher fraction of these high mass early type galaxies, we have our relation being pulled down at higher stellar masses, because these early type galaxies have less angular momentum on average. So this is quite a bit shallower than previous works. One of those previous works is shown here in this blue line, which is the Posty 2018 work, and they find a slope of 0.55 for their work. So we weren't only interested in looking at the slope of our relation, but we're also interested in what drives the scatter. So we believe this scatter to be intrinsic. It wasn't caused by measurement error. So what we did was, in this work, we looked at the relationship between the scatter of this relation and three parameters: bulk to total ratio, H1 gas fraction, and specific star formation rate. And we found that the what drives the scatter in this relation here varied as a function of stellar mass. So for low stellar masses, and by that I mean galaxies that have a stellar mass less than 10 to the 10.25 solar masses, then the dominant driver of scatter was H1 gas fraction, where I've shown that in the plot in the top right panel. And you can see in that plot there the offset of each of the galaxies' specific angular momentum from what was predicted by the best fit relation. And you can see there's a quite strong correlation between the H1 gas fraction and this offset. For high stellar masses, which are the galaxies that are greater than 10 to the 10.25 solar masses, now the dominant driver is actually bulk to total ratio, which is slightly more dominant now than the H1 gas fraction for those higher stellar masses. So in the remainder of the paper, which I wasn't able to show here, we also look into how things change for disk components. So I'd encourage you to have a look at the paper when it comes on the archive soon. Hope you enjoyed it.
Hi, my name is Jess. I'm a PhD student at ICRA UWA, and I'll be presenting my poster Identifying Active Galactic Nuclei Using Spectral Energy Distribution Fitting and the Redshift 0 to 2 Bolometric AGN Luminosity Function. All of this work has been done as part of the DEVILS project. DEVILS is a spectroscopic redshift survey on the Anglo-Australian Telescope designed to have a high completeness at a high median redshift. It's designed to allow us to do group pair and environmental science, and is a precursor for WAVES Deep, a Foremost Consortium survey. As part of DEVILS, we have redone the photometry in our 3 fields and have redone a redshift catalogue in the Cosmos D10 field. So we have about 500,000 galaxies in this field. We've passed these 500,000 galaxies through to our SED fitting code Prospect. Prospect is flexible in the way a user can define the star formation and metallicity histories. For this work, we use a skewed normal star formation history and a linear mapping of mass growth to metallicity growth. So here we show on the left examples of the star formation history, and on the right the metallicity history. We also use an AGN component for this work, so we use the Fritz and Feltra AGN model, allowing for flexibility in the angle of observation, the bolometric luminosity of the central source, and the optical depth of the dusty torus. We define FAGN to be the fraction of flux contributed to the SED by the AGN model between 5 and 20 microns. In this figure here, we show various samplings of the AGN properties in comparison to a no AGN host galaxy. So in blue, we show a blazar-like case where you're viewing your AGN straight through to the central source. The yellow and pink lines show an edge-on case with varying optical depths of the dust torus. Because we've done this through SED fitting, we can also comment on the AGN impact on derived galaxy properties. So we found that due to the degeneracies in fitting the AGN component in your SED, there can be impact in your recovered galaxy properties. We find that there's minimal change in the stellar mass, metallicity, and age, but we find that there's a significant impact to the star formation rates. So if you fit an AGN with a SED fitting code that doesn't include an AGN component, you can be overestimating your star formation rates by up to 2 decks. We've also shown that the AGN identified with Prospect compare really nicely to other methods. So we find that we can recover X-ray selected AGN in good agreement with the X-ray luminosities. We also show that our luminosities agree well with other SED fitting codes designed to get the AGN luminosity and make a lot of simplifications in the host galaxy properties. And we also show that for 51 out of 53 broadline AGN, we can select them as AGN by Prospect as well. And because we have AGN luminosities for all of these galaxies, we can then recover the AGN luminosity function out to Redshift 2.2. And we find agreement at all these redshifts with compiled X-ray, mid-infrared, and optical bolometric luminosity functions from Hopkins, Shankar, and Shen. Here I show the redshift 0.5 case, and you can see that for a lot of the luminosity function, we're in good agreement with previous measurements, but we do turn over at the low luminosity end due to incompleteness. We also are missing AGN with high luminosities due to the very small area of the Devil's D10 Cosmos field, only being 1.5 square degrees. So in summary, with SED fitting with Prospect, we can use it to identify and quantify AGN in good agreement with other methods. When we fit the SEDs of AGN host galaxies, you need to include an AGN component in order to obtain accurate galaxy properties. And using just our SED identified AGN, we can recover the AGN luminosity function in good agreement to previous measurements and theoretical predictions. If you have any other questions, feel free to email me or reach out to me on Twitter. Thank you.
Hi everyone, my name is Jonah and I'm a PhD student at the ANU. And today I'm going to be talking about the Pyxis interferometer. Exoplanets are quite the hot topic these days. We want to know more about their formation history, their demographics, and in particular about their atmospheres and whether they could potentially harbour alien life. Unfortunately, the techniques we use these days, the transit method and radial velocities, aren't really sensitive to Earth-like terrestrial planets around solar-type stars. What we'd really like to be able to do is to directly image these planets and get good spectra of their atmospheres. Unfortunately, that's easier said than done. The resolution requirements to separate these planets from their stars really require long baseline interferometry. However, these ground-based instruments are really insensitive. These stars outshine their planets by a factor of 10 million in the infrared to a factor of 10 billion in the visible, and thus we really need high signal to noise. To get around this, we can move into space and do space interferometry. That is, having a long baseline interferometer in space where you get both the resolution and sensitivity requirements to look at these planets. Space interferometry was studied a fair bit in the mid-2000s, particularly by ESA for the Darwin mission and NASA for the TPFI mission, but these were both cancelled due to budget cuts. There is a bit of a resurgence in the field now, though, with the LIFE initiative, which has been put forward as part of ESA's Voyage 2050 plan. Here at the ANU, we are now looking at building some technological pathfinders with the eventual goal of proving metrology and formation flying subsystems for this eventual LIFE mission. And that's what Pyxis is. Pyxis is a ground-based pathfinder for an eventual CubeSat mission we hope to launch within the decade, to then this final LIFE type mission. So let me go into a bit more detail about what Pyxis is. Pyxis is what we call a car park interferometer. That is, it's going to be 3 autonomous robots in the car park of Mount Stromlo Observatory, which will kind of act a bit like CubeSats. These robots, you can see one of the robots here on my poster, and each one has 3 wheels and 3 actuators to give fine 6-axis control, as well as a 7th gomiometer axis for really fine telescope control. The telescopes themselves are custom made, diamond turned out of solid aluminium, and this negates any thermally induced optical aberrations, which is a particular problem for satellites. We also have an angular control system using a star tracker to give sub-arc minute precision at greater than 2 Hertz to know where you're pointing. And especially important is the distance metrology, and this is the main subsystem we're testing for space. This gives very precise relative distances between the robots using a coarse time-of-flight photodiode system and then a much finer interferometric sensor which can give sub-micron precision using a photonic chip. Finally, the light from the telescopes is sent into a science beam combiner where we hope to get polarimetric and spectroscopic information from these fringes. This is also using a photonic chip based on a tricoupler design. So we're hoping each of these subsystems are being developed here as we speak, and we hope to integrate them all together sometime next year for on-sky testing in 2023. So stay tuned for more updates. Thank you.
Hey, I'm Josh, and thanks for checking out my poster. Here, I'm showing results from a paper we recently published about an unbiased search for polarized radio emission with the Australian Square Kilometre Array Pathfinder. This project was part of the Rapid ASCAP Continuum Survey, an all-sky radio survey at 888 megahertz that has now become the best view of the radio sky at centimeter wavelengths below a declination of plus 41 degrees. We searched this survey for radio sources with high degrees of circular polarization, a property that's only associated with a few classes of astronomical objects, including pulsars and the magnetospheres of stellar and planetary systems. As part of this search, we identified 33 radio stars with a significant degree of circular polarization, including magnetically active M-dwarfs, pre-main sequence stars, interacting binary systems, and magnetic chemically peculiar stars. And 23 of these have never been reported as radio loud in literature. The left plot shows the fractional circular polarization and flux density of these detections, along with 37 pulsars and 6 as yet unclassified sources. We derived lower limits of the brightness temperature of these detections in order to try and constrain the possible emission mechanism. These are shown in the right plot for each variety of star, along with empirical models of the maximum brightness temperature attainable for optically thin, non-thermal gyrosynchrotron emission. While the interacting binary systems are consistent with these models, the majority of our detections are too bright and polarized to be explained by the gyrosynchrotron emission or any other incoherent emission mechanism. They are instead likely driven by a coherent emission mechanism, such as the electron-cyclotron maser, which is responsible for beamed auroral radio bursts from Jupiter and stellar magnetospheres, or plasma emission, which is responsible for a range of solar radio burst phenomena. Both of these processes are excellent probes of stellar magnetospheric properties that are in turn important measurements to aid models of dynamo theory and space weather, for example. This survey detected roughly 1 star per 1,000 square degrees. Future ASCAP and SKA surveys will produce much larger samples, allowing robust statistical properties, such as the burst luminosity function and duty cycle, to be derived. You can scan the QR code if you'd like to check out the paper, and thanks for your interest.
Hi everyone, my name is Juan, and today I'm very excited to present to you part of the research that I'm currently doing in my PhD, which is this high throughput calculation of approximate vibrational spectra, prioritizing potential molecular detections. So the detection of molecules in outer space is particularly appealing when trying to answer questions related to how life began. But the problem is that in order to detect these molecules in outer space, we need very high quality spectroscopic data for these molecules that we often obtain from very time consuming procedures, both theoretically and experimentally. So here I want to present a different approach where instead of doing low throughput, high quality spectroscopic data for one or a couple of molecules, we do high throughput approximate data for hundreds to thousands of molecules simultaneously using computational quantum chemistry. Of course, this data won't be able to allow molecular detections in space because the quality is not as good, but it has other applications that are worth discussing. For this project, we're working with a data set that contains more than 16,000 molecules thought to be potential biosignatures. So basically molecules that might indicate the presence of past or present life on a given planet. And these are mostly small to medium sized molecules, as we can see here in this histogram, where most of the molecules have a total of 10 atoms in total, including hydrogen. So of course we have these 16,000 molecules, so we don't want to perform our calculations manually. So we have sort of like developed this highly automated approach where we have a molecule identifier for each molecule from where we generate initial geometries and then run quantum chemistry calculations that provide us with the spectroscopic data needed that we want. So different applications with this data, but in this poster, I want to focus particularly on 2 applications. So the first one is that we can use this data to disentangle the spectral congestion. So in this figure, we have the vibrational spectrum for 4 potential biosignatures. And what we can see is that, say that we're looking for NO2, and we find that we observe a frequency at 1300 wave numbers, and we can think that that might be NO2, but in this figure we can see that there are other 3 potential biosignatures that also have a frequency that fall within the same spectral window. And in fact, from our data set, there are other 652 molecules that also have a frequency there. So we can use this data to recognize potential misassignments in molecular spectrum. The other application of this data is that we can identify the strongest absorbers in a given molecular group, depending on the intensity of their vibrational frequencies. So for example, here in this table, we have 7 phosphorus-bearing molecules that are of relevancy in terrestrial atmospheres. And we can see that just from the strongest intensity in each molecule, the one in the bottom seems the one to be more likely to be detected. Of course, more studies need to be performed here because we need to analyze the physical and chemical conditions present in the observation source. But this is definitely an excellent starting point for sort of like trying to address these questions. Future directions in this work involves calculating data for conformers, including rotational spectra, because these are particularly important when identifying molecules in the interstellar medium. We can also use this data to train machine learning models for molecular detectability or to calculate vibrational spectra without using quantum chemistry. But I also encourage you to think about like what other applications you think this data may have, and please let me know because we're more than happy to collaborate in this regard. I just want to finalize saying that if you scan this QR code, it will take you to a related publication with we outlining this approach for a particular group of molecules, so phosphorus-bearing molecules. And yeah, so I'm more than happy to take any questions, and thank you.
Hi, and welcome to my poster presentation. My name is Juan Espejo, and I'm a PhD student at Swinburne. And the title of my work is Multi-Resolution Angular Momentum Measurements of Set 1.5 to 2 Star-Forming Galaxies. This work has been done under supervision of Carl Glazebrook, Diane Fisher, and Sarah Sweet. So the motivation of my work is to understand the role that angular momentum plays in the transition from clumpy, messy galaxies in the faraway universe, in particular near the peak of star formation, to the smooth, rotating spirals that we have in the local universe. In order to understand that fundamental role, we need to make precise measurement of the content of angular momentum of these galaxies. But not only that, you also need a proper characterization of the kinematics. Now, most of the kinematic observations that have been done at high redshift have been done using instruments under natural seeing conditions, meaning that they have the effects of the blurring atmosphere, which effectively affect the spatial resolution of your observations. We call this NS for natural seeing. One way to go about this is to use adaptive optics, which allows you to improve the spatial resolution, but it has its own issues. So on one hand, natural seeing has bad resolution, but the observations are deeper, so you can see dimmer objects or you can see the outskirts of a galaxy. On the other hand, adaptive optics has better spatial resolution, but there is a loss in throughput of the light, so you have effectively less signal to noise. So ideally, you could combine these two observations of the same galaxy, and that's what we do with our method. We have developed a method to combine the NS and AO data of a sample of 10 galaxies from KMOS, OSIRIS, SYMPHONY, as well as the photometry from HST to measure the angular momentum content of these galaxies above a redshift of 1.5. The method consists of creating a model data cube with the kinematic parameters, which is convolved separately with the different PSF shapes. Once you do that, you extract a velocity field from those data cubes and you compare it with the input data. And then you can obtain the best kinematic model. This is all based on ionized gas kinematics. Additionally, we also model light distribution to estimate the stellar mass, which allows us to calculate the specific stellar angular momentum of these galaxies. We pay special attention to the PSF modeling because the AO-PSF has a core and a broad component, which we model in high detail, which you can read in the paper. We show that combining the two resolutions actually decreases the uncertainties, and now that we have the best measurements, we put them in context with other studies. So in this plot, we have the fold relation, which is the relation between stellar specific angular momentum and stellar mass. And we see that the scatter of our galaxies is consistent with the scatter from previous studies at high and low redshift. This means that you can trust studies at low resolution if those galaxies are actually disks. The main results of this work, which can be read in this paper, are that first, combining the two resolutions allows you to decrease the uncertainties in the measurement of J star. Second, the main source of systematics in this measurement is actually the choice of surface brightness model, which has to be quantified in detail. And third, the results from previous low-resolution studies can be trustworthy with the caveat that there has to be a proper kinematic classification. Thank you.
Hello, this is Kai from the University of Sydney. Here is some result for field solar eruption. This small flare occurred near the solar disk center. The subside of the act regions shows sunspot motion. We can find the rotation of the lower left spot and the strong shear flow between the top and middle spot in the right panel. This shear flow builds energy of this act region and drives the small flare. Here is the observations from the AIA EUV measures. It's very clear to figure out at the initial stage, some brightenings occurred at the foot point of the flux rope, and then the rope experienced a sudden rise and then stopped. We modeled the field eruption by a data-driven simulation, which is initialized by a nonlinear force-free field. 3 different popular methods give similar results and are comparable to the observations. All of them give 3 flux ropes and they twisted with each other. Observed solid ferric magnetogram are used to drive the simulation, and also the bottom plasma velocity is inverted by using the Dave4VM method. They're filled into the ghost layer to drive the simulation, and then we use the open source code MPI-MWalk to solve the full MHD equations with the solid gravity and optical thin relative cooling. From the simulation, only the top part of the twisted structures shows a sudden rise, and the lower one seems very stable. This structure seems to correspond to the stable structures in the AIA 304 channel indicated by the blue arrow. Comparison between observations and the simulations shows some corresponding features. For example, the twisted and the fibrillary structures from the H-alpha in the top panel. In addition, the quasi-substrate layers at the bottom correspond to the observed flare ribbon in H-alpha observations, especially the spiral one, which is a typical Hawk structure around the foot point of the flux rope. Several ball patches are found in the simulation. Their reconnections correspond to the H-alpha brightenings. The brightenings number 1 in H-alpha observations come from the magnetic reconnection at this ball patch. The number 2 come from this ball patch, and we can also find a current sheet whose magnitude is indicated by the color in the left image. The brightenings in number 3 comes from the magnetic reconnection at this ball patch. The 3 brightenings indicate that the initial magnetic reconnection occurred at several different ball patches during the initial phase of this field eruption. The final stage in the simulation gives highly mixed and twisted structures in this act region. The color in the left figure indicates the magnitude of the electric current. It's clear that the final stage still contains multiple flux ropes, and the right one shows the same structure, but the color indicates alpha values. This value is a local index for the magnetic chirality, which is clear that different twisted field lines are contained in the final stage. Here is a brief summary of our research. Thanks.
The MAGPIE survey is a large program being run on ESO's VLT. We are using MUSE to observe galaxies at redshift 0.3, resolving the kinematics of galaxies at a period of rapid transformation. MAGPIE also has an active theory component to the survey. We're working directly with several of the largest cosmological hydrodynamical simulations in the world, including EAGLE, Magneticum, the Taylor and Kobayashi simulations, Illustrious TNG, and Horizon AGN. While all of these simulations broadly reproduce the observable universe, they get there in very different ways. If we plot the evolution of kinematics in each simulation as shown here, we see very different stories. The purpose of the theory stream of MAGPIE is to investigate these differences between our models in detail, to understand the reasons for these differences, and to compare and update our subgrid physics to reflect the MAGPIE galaxies that we observe. It's important that we make these comparisons consistently. To do so, we're building mock observations for all simulated galaxies, such that we can compare to one another and our MAGPIE observations. We are using the open source code SimSpin to create these mocks, and plan to generate a full suite of theory data products for release. This will include projected gas property maps, such as star formation rates and metallicities, We'll also be generating the projected stellar properties, both in mass and luminosity weighted formats. Finally, we can use SimSpend to produce full spectral cubes in FITS format, which can be used with our observational pipelines, for example, fitting the kinematics with PPXF. For more info about the MAGPIE survey, check out Emily's talk in Parallel Session 2 on Monday, and keep an eye out on the archive for theory data products coming soon. Thanks.
The host galaxies of fast radio bursts as seen by the Very Large Telescope. My name is Lachlan Marnock, and I'm a PhD student at Macquarie University. My supervisors are Stuart Ryder, Richard McDermott, and Elizabeth Mahoney, and I am working on fast radio bursts with the Craft team. Fast radio bursts are bright, brief radio pulses from other galaxies. Although we don't know yet what causes them, they continue to be very useful in probing extragalactic matter. To really understand the information encoded in an FRB, some understanding of the host galaxy is required. Given how distant and faint these galaxies are, this is often a job for an 8-meter telescope. So far, only 15 FRB hosts have been published, 9 of which are identified by CRAFT, the Commensal Real-Time ASCAP Fast Transient Survey. Here we present VLT FORS2 imaging of those 9, along with an additional 2 with publication in preparation. First we have the FRB host that started it all. Although it wasn't the first FRB host on record, we have the repeater FRB 121102 to thank for that. It was the first localized from a single burst, and the first traced to a massive galaxy. 180924 showed us that FRB hosts don't all look like the intensely star-forming dwarf host of the first repeater. In fact, the repeater host turned out to be an outlier in the host population, most of which seemed to be fairly ordinary, like this fellow. This FRB passed through the halo of a foreground galaxy, lurking in the north of this plot. This offered a direct insight into the halo's magnetization, density, and turbulence. All 3 were found to fall short of prior expectations, raising numerous questions about galaxy feedback mechanisms. 1906-08 was exciting because it was the first time we saw a detailed spiral galaxy, complete with arms, bulge, and bright nucleus, when we pointed a telescope at an FRB. This is not unexpected, and we are beginning to suspect that FRBs might have a preference for showing up in spiral arms. However, it was an exciting moment. Speaking of spirals, how about 2 for the price of 1? This pair of possibly interacting galaxies makes a spectacular addition to our gallery of hosts. Originating only 2 arc minutes on the sky from Fomalhaut, a first magnitude star and the 19th brightest in the sky, and now my declared nemesis, this host presented something of a challenge for a ground-based telescope. Masking the bottom chip entirely, we still had the glare to deal with. I took the individual exposures and fit a polynomial to a rectangular patch centered on the host, then subtracted this model from the patch before co-adding the frames. To check the effect this process would have on the photometry, synthetic sources of known brightness were inserted and recovered. This gave us the tiny 20-second magnitude host galaxy in the center there. Although there's not much to say about our other galaxies, just yet, together they begin to build up a sample from which we are learning a great deal about FRB hosts and environments in general. For more information about Craft FRBs, their hosts, and the exciting research we're doing with them, please see our publications. Thank you.
Welcome everyone. My name is Marcin Sokołowski and I am from Curtin Institute of Radio Astronomy, KAIRA. I would like to present our poster about high-speed all-sky monitor for fast radio bursts and techno signatures. Since the last year publications by LOFAR and Greenbank telescope groups, we know that fast radio bursts or FRBs can be detected down to 100 MHz frequencies. Therefore, the main goal of our project is to develop an all-sky monitoring system capable of detecting FRBs and signals from extraterrestrial intelligence in high time resolution millisecond images of the entire hemisphere, so-called all-sky images, as the examples in the slide. These images will come from prototype stations of the low frequency component of the Square Kilometre Array radio telescope, SKA low, which can observe at frequencies between 50 and 350 megahertz. Two prototype stations of the SKA low, the Aperture Array Verification System 2, AAVS2, and the Engineering Development Array 2, EDA2, have been operating at the Murchison Radio Astronomy Observatory for the last 2 years. The images of the stations are shown in the slide. They have been used mainly to verify performance of various hardware and software components and compare the overall performance of the stations, such as the station sensitivity, against the SKA low specification and simulations. Although the sensitivity of the stations is currently limited by the small observing bandwidth of about 1 MHz, we collected hundreds of hours of all-sky images in 2-second time resolution, and we use these images to demonstrate the potential of the stations for all-sky transient monitoring. The results of this preliminary results of these studies were published earlier this year in PASA. We applied difference imaging technique to 2-second all-sky images, and we identified, besides other things, we identified extreme activity from the nearby pulsar B0950+08, which lasted for about 3 hours, and the radio transients from this pulsar were reaching flux densities of the order of 160 Jansky, which is about 65 times more than the mean flux density of the pulsar. Examples of bright transients from the pulsar are shown in the image here. Unfortunately, we did not find any FRBs. However, during our observations, 1 FRB was detected by ASCAP and 2 by Deeper, Wider, Faster. Although we did not detect low-frequency counterparts of these FRBs, we published an astronomy telegram with upper limits on their fluence at 160 and 230 MHz. And even these non-detections demonstrate the power of such an all-sky monitoring system. That is, if an interesting astrophysical transient, such as, for example, a gamma-ray burst or a gravitational wave event, is detected by other instruments, we should be able to provide high-time resolution images of the sky before, during, and after such an event. Therefore, we are currently working towards increasing the observing bandwidth to about 40 MHz and generating millisecond images, which will increase sensitivity to FRBs and technosignatures by about 2 orders of magnitude. And this upgrade should enable detections of tens or maybe even hundreds of FRBs per year and convert at least one of the stations into an FRB survey machine. It will also help to firmly establish FRB rates at frequencies below 350 MHz, which are currently highly uncertain. The realization of these goals will require significant improvements in the processing software. Therefore, we are looking for a PhD student to work on novel algorithms and software for FRB searches in high field or in wide field and all-sky high-time resolution images from the SKA low precursor and prototype instruments, including the Murchison Wide Field Array. Hence, if you are an interested person or you know someone who might be interested in this project, please get in touch with me as soon as possible. This is our poster, and thank you very much for your attention.
Hello, my name is Mark Casali, and I am Director of the AAO at Macquarie University. And I'd like to welcome you to this short presentation in which I will reintroduce our instrumentation consortium under its new name of Australis. I'm doing this on behalf of the other node directors, Francois Rigaud at the ANU, AITC, and Julia Bryant at the University of Sydney. As you may be aware, there was a new teaming up of Australian instrumentation teams in astronomy in July 2018 between the 4 groups that you see on the slide there. The idea being that we were trying to build a consortium with the size and skills necessary to build the new generation of infrared and optical instrumentation for 8-meter and larger observatories. The name adopted then was AAO Consortium. However, to cut a long story short, confusion remained in the community over that AAO name. So to resolve this, we have now adopted a new name of Australis. So you should be seeing this from now on in all contexts involving the consortium. But enough about the name, let's move on. The consortium has over 100 engineers and scientists spread across the 3 nodes. And one thing we've been trying to do over the last 3 years is pay a lot of attention to coordinating our processes and ways of working, documentation, etc., so that we can mesh together and work together as smoothly as possible. The area we've really been focusing on is where our traditional strength is, and that's in the area of optical infrared instrumentation for astronomy. But that covers really every area in optical infrared instrumentation, from optics through to detectors, software, hardware, computers, etc. The Australis Consortium currently has an almost exclusive, or certainly a very strong focus on our partnerships with ESO and GMT, and this follows directly from the Astronomy Decadal Plan and the emphasis placed on these associations by AAL, our funding agency. Very importantly, however, income from these is not sufficient to maintain the Australis nodes at their current size, so we're actively seeking out all the time other opportunities, such as building instruments for other observatories, or even developing adjacent areas of expertise in fields such as space or remote sensing. And one thing that's very important to remember is that the optical IR instrument development for major observatories such as ESO results in the return of guaranteed time for the Australian astronomical community, and also supports our membership of the organisation, in that case ESO, and advances high technology initiatives in Australia, an area that's very important for us to pay attention to. You can see here a list of current active projects and potential future projects for ESO and GMT. Most are for ESO, and you'll recognise there our flagship project MAVIS, the AO-fed visible imager and spectrograph, which is actually led by Australia. You might recognise ESOP, our fibre positioner that we've built for the Foremost survey facility, various projects for GMT as well. And we hope that all of these will be just the beginning, and that there'll be many more to come in the future. Unfortunately, my time is just about up. I can't cover very much more. So all I can say is thank you for watching.
Hello, my name is Melanie Ross, and thank you for the opportunity to present on my poster, The Life and Destruction of the Adelaide Observatory West Terrace, a personal exploration. So I'm a creative writer in the Creative Arts Honours Program at Flinders University, and my supervisor is Amy T. Matthews. A special thanks to Paddy McGee from University of Adelaide for his support of the project and specialist knowledge, and also a mention to Gavin Rowell, also from the University of Adelaide, for his encouragement and support. So to be brief, I've become intrigued with this lost place, the Victorian architecture, the grounds and the activities that happened there. And we know that this place was vital to early Adelaide, and we can recognise its contributions to astronomical history. However, there has been little focus on the architecture and grounds of the site. And unfortunately, in many mainstream South Australian historical texts, the observatory is missing altogether. So through my writing, I'm seeking to recreate this site so I can explore it, not only for myself, but also for the reader. And as part of this, I'll be mapping my emotional connection to this place through a humanistic geographical perspective. And this project is currently in the reading or research phase. So I have 2 research questions. How can this demolished and erased site be made visible, in quotation marks, again through literature? And how can literature explore human connection to a place that no longer exists? My project is creative non-fiction, and it's a hybrid that combines the creative response to my research, which is archival, looking at interdisciplinary works and secondary sources, but it also combines my findings as I write through the creative process. My reflections, my imaginings, decision points I make, and challenges I face along the way.
So I've included a timeline on my poster of the buildings in the site. However, I'm also looking at other details like the fencing, the planting, and other events, other changes that were happening in the parklands surrounding the property. At this stage, though, as we know, theses can change as they go, I have 4 components. I look at the place in terms of architecture and the history of the building's grounds, looking at the objects and artefacts, because we understand a lot about a place from what is left behind. And in particular, I'm reflecting on the 1881 Troutman and Sims Transit Circle, the 8-inch Cook Equatorial, the McLean Star Spectroscope, also the first observations, the Transit Circle by Charles Todd, and the visitors' books where thousands of people wrote their names and impressions of the place. I'll consider the destruction, demolition of the site too, but all of this contributes to a reconstruction of the place where I can imaginatively wander and explore it. I'll be supporting the reader to connect with this place through my first-person narration and engaging lyrical poetic style, and also using fragments of prose and blank space on a page to encourage reflection and pause. And I'll be including the limited photos I have available and site plans so people can connect with the place and also to validate some of my content. And the completion date is due for June 2022. Thank you for your time.
One major priority in radio astronomy is understanding the early universe formation history. Although the cosmic microwave background, or CMB, that results for the Big Bang is well measurable, the epoch that followed, due to neutralization of ionized gas from the CMB due to its opaque nature, is not. This period is also known as the Dark Ages. However, one can infer Dark Ages characteristics by looking at the differential temperature between the CMB and the cosmic dawn, the epoch where the first stars started to form, sparking the epoch of reionization, which led to the full reionization of the universe. Understanding these epochs can lead to a wealth of information and give us more insight in the formation history of the celestial bodies we see around us today. One way to probe for these first stars, for example, is by probing the 21 cm hyperfine electron spin flip transition line from neutral hydrogen, where a change in electron spin state emits a radio wave of 21 cm wavelength. However, measuring the 21 cm line is not trivial, as it's formed by extragalactic and galactic foregrounds before receiving it with a radio telescope system. It is hard to disentangle these foregrounds, as they are around 3 to 5 orders of magnitude higher than the signal we desire. One way to combat this is through the generation of multiple sky maps, spanning a wide range of frequencies and angular scales. These maps can then be used to generate a foreground model to abstract from the 21 cm background signal. However, although smaller angular scale point source foregrounds are relatively well defined, low frequency diffuse foreground emissions, especially on the southern hemisphere, are not. This is mostly due to the complexity of solving the three-dimensional interferometric measurement equation, which is often simplified using a flat sky approximation, allowing one to Fourier transform between the visibilities the system sees and the intensities in the sky. However, this results in a loss of wide field accuracy, as well as the ability to measure the full sphere, since one can no longer distinguish points exactly opposite on different hemispheres. As a result, we are forced to use more complex methods to image the full sky, such as mosaicing, which is often a time-consuming and strenuous process. Instead of assuming a flat sky, one could also use spherical harmonics to solve for the measurement equation instead. Much similar to how the Fourier series operates on the boundaries of a circle, spherical harmonic-based functions operate on the surface of a sphere. These basis functions can be split up in 3 distinct types: zonal, tesseract, and sectoral harmonics, which depend on the spherical harmonic order L and rank M. Shaw et al. Noted that when looking at Earth's periodic rotation over a sidereal day, one could notice sectoral harmonics operating in the same rotational plane. These harmonics are only rank M dependent and do not mix on the sky. We can utilize these characteristics through employing wide-field, center-pointed radio interferometers performing transit interferometry, measuring the sky passing overhead. This way, we can measure the full sky within a day's time frame, whilst maintaining exact wide-field effects. Fourier transforming the visibilities with respect to M allows us to describe the visibilities as M modes on an M by M basis, If you then also expand the system characteristics or beam transfer function and sky into spherical harmonic coefficients, you can reduce the measurement equation to a simple linear equation. Solving for the sky in this case would simply be inverting the equation. Using this method with the Engineering Development Array tool, the Whitefield Radio Telescope in Western Australia, we presented a 159 MHz MO generated sky map. This map is created with two 24-hour observations to remove the sun from our sky image. The map has a 3-degree angular resolution and is supersampled on a 1-degree pixel grid. The Northern Hemisphere is fit using a rescaled version of the updated D-Source Tesla map by Ramazayas et al. This map is the first in a series of EDA2 generated diffuse southern sky maps, with goal to help better constrain a diffuse foreground model, and will be made publicly available once published.
Hello, my name is Miguel Gonzalez, and I'm a PhD student from Macquarie University. Today, I'll talk about my group research on common envelopes. This work is focused on simulating these systems using a thermally pulsating AGB star as a donor for the envelope. Our main goal was to figure out whether or not a common envelope can be triggered during a thermal pulse. These pulses are characterized by a sudden expansion and contraction of the star that lasts a few centuries due to periodical helium flashes. We also wanted to compare the post-common envelope system with that of a similar donor, albeit in the RGB phase. Finally, we want to analyze the influence of recombination energy and radiation pressure in the common envelope. For this, we create and evolve a 2 solar mass star using the stellar evolution grid code MESA until it reached the thermal pulse AGB phase. Then we map it into the SPH code Phantom and put it in orbit with a 0.6 solar mass same particle. The simulation was run from Roche-Low overflow until it reached a self-regulated phase. We run 4 simulations. The first one with an ideal gas equation of state at low resolution. The other 3 were run at high resolution with an ideal gas equation of state for one, ideal gas plus radiation pressure for the other, and a tabulated equation of state for the fourth. This last one takes into consideration the recombination energy of the gas. The animation showed the simulation with high resolution and ideal gas equation of state. The spiral phase occurs at 15 years and the self-regulated phase at 20 years. We found that the 4 simulations end at roughly 28 solar radii, giving away the same orbital energy to the gas. The simulations suggest that the common envelope may take place during the thermal pulse, but since the Roche-Low overflow phase timescale increases with resolution, its convergence may be at a time longer than the duration of the pulse. The still image in the left column shows the morphology of the common envelope from our system as opposed to one using an RGB star as donor, which indicates that its evolutionary phase affects the post-common envelope shape. Only the tabulated equation of states unbound the whole envelope, but in all cases, the binary survives. This confirms previous works in which the recombination energy is needed in order to unbound the system. Thank you for your attention.
This is my ASA poster talk. I'm talking on the cosmic atomic neutral hydrogen gas density evolution. I'm Philip Lahr from the ANU. This is the sublimation rate density versus a function of look-back time. You can see it increases by a factor of 10 at the peak of star formation, at about a factor of look-back time of 10. This is the cosmic H1 density versus look-back time. Low redshift is well determined by the H1 21-second emission measurements and high redshift by damp moment alpha absorption measurements. You can see it increases by a factor of 2 at its peak. The purpose of this talk is to try and explain why this only increases by such a modest amount compared to the star formation rate density, which increases by a factor of 10. You can look at the star formation rate versus H1 mass at low redshift. The blue galaxies are for normal galaxies, and they have a parallel fit of this form. Now you can estimate the H1 density, so the H1 mass density, from the star formation rate density using this formula here, where gamma is the incomplete Euler gamma function, and star formation rate star phi star alpha of the star formation rate density Schechter function parameters from Kazuchi et al., and using the parallel relation between star formation and H1 mass, we get the A and the M from. This is the cosmic H1 density versus look-back time, now on a log scale. The black points are the normal galaxy, are the measurements. And you can see these are the blue points are the estimated values from star formation rate density. And you can see they greatly overestimate the amount of H1 mass you expect at any given redshift. What this is saying is that the relationship between H1 mass and star formation is not the same at higher redshift. This is that relationship at low redshift, star formation versus H1 mass, and the blue points are the normal galaxies, but up here you have the red galaxies, which are starburst galaxies. And they're much more efficient in much more higher star formation rate for the H1 mass. They are much more efficient in converting H1 mass into stars and normal galaxies. At a 10 years look back time, about theta equals 2, the number of galaxies classified as ULERGs and LERGs increases by a factor of about 15. So being rare exceptions as in the present day universe, at the peak of star formation, such galaxies are found on the star forming main sequence. These high star formation galaxies are likely to have H1 surface densities at or exceeding the self-shielding threshold, and so have increased efficiency in converting their H1 gas into molecular gas, like local starburst galaxies. So in conclusion, the reason H1 density only shows modest evolution is that the star formation at high redshift is more efficient in converting H1 gas into stars than at low redshift due to the presence of more ULERGs and LERGs.
Hi everyone, my name is Rami El-Shalami. I'm a PhD student at the University of Adelaide. I work with Gavin Royals and Sabrina Enig. Here I'm presenting my poster about the investigation of the multi-degree long outflow toward the Scutum supershell. We investigated this region using WAM data and optical H-alpha. The spectral cube from the WAM data indicate a distance toward the gas around 2 to 3 kiloparsec. Using that distance, we estimate that the minimum length of this outflow is around 70 parsec. We investigate also the luminosity of this outflow using SHASA, VTSS, and WAM surveys. We found out that the luminosity of this outflow is around 10 to 36 erg per second. This high luminosity indicates powerful source generating this outflow. We use the path shock morphology to indicate its velocity by getting the opening angle of that path shock and using Mach angle. This gives us 21 to 32 km per second as the velocity of the path shock. This gives us an upper limit age for this outflow of 4.5 million years. We discussed the potential origin for these sources. A young stellar object toward this region should be around 30 parsec, due to the fact that young stellar object outflows are extended to 1 parsec. We didn't see any young stellar object toward this region. The pulsar proper motion faster than ISM's velocity of sounds produce a path shock, and also the pulsar rotation can produce an outflow. Stellar wind from OB stars could also generate a path shock. We searched for OB stars toward the path shock and we couldn't find any. A supernova can produce an outflow. Therefore, we search all compact objects toward these regions and we use the limitation of below 5 kiloparsec distance and 10 million years age to limit the pulsars. We found some pulsars, however, most of these pulsars are regular pulsars. Likely, we have seen that the most energetic point source in this region is LS5039. The birth location of the LS5039 is discussed by Modlin et al. 2012. They suggest 2 birth locations for this macroquasar, one of which is in a good alignment with this outflow, and a nearby source for this macroquasar is a Wolf-Rayet 115. The existence of such a source indicates that there is an old stars at late age of life. Here we show in all the parameter of this outflow at 2 degree long and if it's related to LS5039. We conclude as this outflow should be related to energetic supernova, and LS is the best candidate that we see in this region, and lately the compact object suggested to be a magneta. So based on our investigation, we speculate that this outflow produced by long gamma ray burst related to the compact object in the binary system. Thanks.
Hello, my name is Rebecca and I'm a PhD student at the University of Queensland. Today I'm presenting my research on the formation of the smallest galaxies. Ultra-compact dwarf galaxies, or UCDs, are intermediate objects between globular clusters and dwarf galaxies. It is believed that UCDs are either massive globular clusters, the high mass end of the globular cluster mass spectrum, are in particularly massive galaxies, or that they are the strip nuclei of dwarf galaxies that were disrupted through interactions with other, more massive galaxies. In this study, we used the hydrodynamic Eagle simulations to test if UCDs formed by the tidal stripping model in massive Virgo-like clusters. To identify galaxies which may be stripped, we searched the merger trees of galaxies and clusters. We modify the simulations by defining the central most found particle of nucleated galaxies as the nucleus and tracking it through the simulation. The redshift zero positions of these most found particles are then determined and their properties are derived. In our first published paper, we determined the numbers, masses, and distributions of our sample of simulation nuclei and compared them to observations of UCDs in the Virgo cluster. Figure 3 shows that the number of massive UCDs found in Virgo is consistent with the number of massive strip nuclei we predicted to contain. Figure 4 shows that the radial distribution of strip nuclei around a massive simulated galaxy is consistent with the radial distribution of UCDs around M87, a massive galaxy in the Virgo cluster. Therefore, our results show that the strip nuclei can explain the numbers and radial distributions of UCDs in Virgo. In our second paper, we determined the internal properties of our sample of simulated strip nuclei and compared them to observations of UCD properties. Figure 5 shows that the simulation predicts strip nuclei colours are consistent with the colours of observed UCDs in Virgo. One consequence of UCDs being strip nuclei is that they are likely to retain the central supermassive black holes found in galaxy nuclei. Figure 6 plots the supermassive black hole masses of simulated strip nuclei against their total masses and compares them with the studied supermassive black holes in observed UCDs. We find that the simulations accurately predict the expected masses of supermassive black holes in UCDs, a strong test of the simulations that establishes that they are predicting accurate results. In Figure 7, we compare the number of galaxies that will have been disrupted to form strip nuclei with surviving galaxies in a simulated cluster. We find that the expected number of supermassive black holes in strip nuclei depends on the occupation fraction of black holes in low-mass galaxies. Assuming pessimistic occupation fractions, strip nuclei represent a minimum increase in supermassive black holes in galaxy clusters of 30%. In conclusion, our new model of UCD formation shows that the tidal stripping of galaxy nuclei can form the observed UCD populations. High-mass strip nuclei have consistent numbers, distributions, and colours with UCDs in Virgo. The simulation reproduces the expected supermassive black hole masses of observed UCDs, and we find that the strip nuclei contribute a large number of supermassive black holes in galaxy clusters. Therefore, there is a high probability that UCDs form from the disruption of dwarf galaxies. Thank you.
everyone. Thanks for joining me for this short video describing my poster, What Can We Learn from Lithium-Rich Giants in Galah? I'm Sarah Martel from the University of New South Wales, and the work I'll be talking about was done in collaboration with Jeffrey Simpson, Aditya Balasubramanian, and the Galah survey team. Galah is a large spectroscopic survey that we've been running at the AAT since the end of 2013. And so far, we've observed over 700,000 stars. Most of those are analyzed and available in our latest data release, Galah DR3. As a galactic archaeology survey, we focus on the stars that can tell us the most about the history of the Milky Way. We have a very thorough sample of the nearby disk. And for all of our stars, we derive important quantities like ages, kinematics, and the abundances of 29 key elements. The project that's the subject of my poster is looking at lithium-rich giant stars in Galah. Lithium is an interesting element because it's produced in Big Bang nucleosynthesis, but almost every process after that destroys it. This includes stellar evolution, so stars begin their lifetimes with the same amount of lithium as in their local ISM, but it's destroyed as time goes on. This diagram from Lin 2009 shows the lithium abundances for stars in the globular cluster NGC 6397. And this is what we expect lithium abundance in stars to do over time. As stars evolve, they move to higher luminosities, lower surface gravities, and their lithium abundances drop smoothly. Around 1% of the time, though, evolved stars like red giants have high lithium abundances, sometimes even higher than the Big Bang nucleosynthesis level. There have been a number of different mechanisms proposed for how to produce that lithium, and a lot of literature with small observational data sets that evaluate which models make sense. But we really need a broad enough sample of lithium-rich giants if we're going to understand which mechanisms are actually responsible for this lithium production. What we've done in our project is to go looking for lithium-rich giants in Galah to see what we can find. Here's the Galah version of this diagram, and you can see that a small fraction of the stars have quite high lithium abundances. What we find is that there are 4 distinct kinds of lithium-rich giants, and we can see them all in this diagram. There are luminous red giants, which are expanding and may gain extra lithium by engulfing their gas giant planets, or they may produce it internally. Red giants at the luminosity function bump, which have just had fresh hydrogen mixed into their hydrogen-burning shells, and their internal structure is re-equilibrating. Red clump stars, which have already been through the giant branch phase. They've had a helium flash to ignite core helium burning and are re-equilibrating after that. They can also be affected by tidal torques from a binary companion. And the secondary red clump, which is for stars that are a little more massive and started their core helium burning without a big flash event to disturb the interior structure. We already know these stars are rare, and there's a lot of literature on possible trends between lithium richness and metallicity, evolutionary phase, binarity, and rotation. What we learned from the Galah data is that the probability for a red clump star to be lithium rich is over twice the probability for a red giant branch star, which may mean that there are separate processes at work in the two groups. That the probability to be lithium rich is higher for higher metallicity stars, with a smooth increase for red clump stars and a sudden jump at solar metallicity for red giant branch stars. This indicates that the internal structure of the stars, which is less compressed at high metallicity, may control how easy it is for lithium to be internally produced or transported to the surface. That rapid rotation is correlated with high lithium abundance in red clump stars specifically, which might support the idea of rotationally driven mixing, or it might be a sign of tidal interactions with a binary companion. So that was a pretty quick tour of what we did in the paper. If you want to see all the details, I'd be happy to talk to you about it, and you can read the whole thing in the monthly notices, volume 505, page 5430. If you want to get the Galah DR3 dataset with all the spectra and the catalogs of stellar parameters, abundances, ages, and kinematics, you can get those at galah-survey.org. And if you want to see regular updates from the team, you can follow us on Twitter. Thanks so much, everyone. I'll talk to you later.
Hi there. My name is Simon Lee, and with Sabrina and Gavin, I've been doing work based on the idea of a Cherenkov telescope ring. This would be a network of Imaging Air Cherenkov telescopes, or IACTs, based all around the world using pre-existing and new sites to provide full sky coverage for observing GeV and TeV gamma rays. A site in Australia would help fill in the current coverage gap in the Southern Hemisphere. My work has been to investigate what kind of performance one could expect from an Australian IACT site and see how it would be affected by altitude, the number of telescopes, their size, and how they are arranged. The motivation behind the Cherenkov telescope ring is to improve our ability to follow up on observations of transient phenomena and to observe sources continuously as their visibility passes from telescope to telescope. AGN flares seen in other wavelengths could trigger instantaneous follow-up in TeV energies at any time. Multi-messenger studies could be assisted following up on neutrino and gravitational wave detections. Uninterrupted observations of sources across days would allow for better time-dependent spectral energy distributions and an increased chance of seeing orphan gamma-ray flares. To compare the performance of different setups, simulations of extensive air showers from gamma rays and cosmic ray protons were made. These were fed into telescope simulations based on the designs from the Cherenkov telescope array of both the 4-meter small-size telescope, or SST, and the 12-meter medium-sized telescope, or MST. Random forest models were then trained on subsets of this data to reconstruct the energy, direction, and gamma-ness of showers, and then applied to the remaining data. Here are some performance results. Sites were tested at both 0 meters and 1,000 meters above sea level, as Australia has a limited selection of high-altitude sites available. The 1,000 meter sites do slightly better at lower energies, seen here with a lower energy threshold. Conversely, the ground-level sites had better performance in high energies, including a larger effective area. Wider distances between telescopes showed noticeably better angular resolution. A modest improvement was seen with 2 telescopes increasing from 80 to 277 meters apart, and we saw twice the resolution for setups of 3 to 4 telescopes arranged in a triangle when doubling the baseline from 139 meters up to 277. For a setup of 4 MSTs, we saw angular resolution down to around 0.05 degrees. Effective area and sensitivity also saw improvements. Here we compare MSTs to SSTs. With effective area, we saw one MST have a larger effective area than any of the SST setups we tried. Angular resolution was comparable for a given number of telescopes, with a slight advantage to MSTs. And here's an example of sensitivity versus observation time at low energies comparing 2 MSTs to 4 SSTs. With these 50-hour differential flux sensitivity plots, we can see large jumps in sensitivity with more telescopes. And as expected, all the different MST setups extend to much lower energies than the SSTs, but perform about equally at the very highest energies for an equivalent number of telescopes. Below 10 TeV, we saw one MST having equal or better performance than 2 SSTs, and 2 MSTs having equal or better performance than 4 SSTs. The construction and maintenance of these two designs is of course very different, and in future these performance comparisons can allow for informed decisions to be made about a site design. In summary, an Imaging Air Cherenkov telescope site in Australia would help contribute to the study of transient and variable astronomical phenomena in the very high energy regime. In our study, site altitude wasn't seen to contribute significantly to performance, given the limited available height in Australia. Wider telescope baselines gave better performance across the board, especially in angular resolution. Large performance jumps were seen with more telescopes, and we can now make performance comparisons between different numbers of MSTs and SSTs. Thank you very much.
Hi, my name is Tiffany Collins, and I am from the University of Adelaide. If you are unaware, HESJ 1825137 is the most powerful and luminous TeV gamma-ray pulsar wind nebulae. This makes it an excellent laboratory to study particle transportation around pulsars. This presentation is a status report on modelling transportation of electrons from powering pulsar PSR 1826-1334. Just to give you an idea of what the system looks like, here is an antenna CO12 data in velocity range 40 to 60 kilometers per second. This corresponds to a distance of 3.5 to 4.5 kiloparsecs, with the pulsar being located at approximately 4 kiloparsecs. The Hess significant contours towards HESJ 1825137 can be seen in dark green, with the powering pulsar PSR 1826-1334 shown in pink. The red region describes a region towards neighbouring unidentified object HESJ 1826130. The HESJ 1825 equivalent Hawke and Lasso regions are shown in black and brown respectively. Both equivalent sources have recorded photons with energies above 100 TeV. Another interesting thing to note is that the equivalent sources are located between HESJ 1825 and HESJ 1826130. This poses interesting questions about the system. For example, how much is HESJ 1826 contaminated by HESJ 1825? And is HJ1825 and or HJ1826 a pevotron, where a pevotron is an object able to produce cosmic rays in the PeV energies? In an attempt to solve these questions, the region towards HJ1825 will be modelled with the pulsar as the source of electrons. Assuming a simple case of isotropic diffusion of high-energy electrons, the energy distribution can be described by this equation you can see on the right. The first term describes the diffusion of high-energy electrons in a particular region. The second term considers losses due to radiative processes such as inverse Compton, Bremsstrahlung, and synchrotron interactions. And the final term is simply a source term for particle injection. To numerically solve this, the region towards HJ1825-137 will be split into a 3D grid of cells, which you can see to the left. The 3D grid will then be used to model the density, magnetic field, and soft photon fields, for example, towards HJ1825-137. Each cell allows electrons to be transported in and out to neighbouring cells. After integrating the equation on the right over the age of the powering pulsar, the spectral energy distribution and radial profiles of HJ1825-137 can be predicted, which is shown on this slide. The top left shows the X-ray radial profile towards HJ1825-137 for photons with energies between 1 to 9 keV, while the top right shows the gamma ray radial profile with photon energies between 0.2 and 90 TeV. The predicted profiles are shown in black, which is then compared to the observed data as seen by Suzuki and Hess in red. The bottom left image and the bottom right image shows the predicted spectral energy distribution towards HJ1825 and HJ1826 respectively. As you can see, the model is able to predict the radial profile shapes of both the X-ray and gamma ray data, and also the spectral energy distribution of HJ1825-137 is an approximate match, but further tuning of the model is needed to get an even better match. So thank you for listening to this short presentation. Please keep an ear out for further results. I'll leave you with this slide of my poster.
Hello everyone. Today I'll talk about the poster which is related to an ASCAP discovery of a quite interesting source. It is highly variable and circularly polarized and in the direction in the large machine learning cloud. So lots of possibilities related to it. Could it be an extreme brown dwarf, or maybe it is a new magnet? This target is found in the ASCAP VAST data. So VAST is a survey for searching for variables and transients using the ASCAP telescope. We searched variable and transient events in 230 square degree field, and we found 20 variable sources, but one of them is quite unusual. So I just listed some properties in here. It is located in the LMC field, but we don't know like the distance, so we are not sure if it's within the LMC or just in that direction. And second, it is highly variable. So here is the light curve. You can see it's like the flux density is from about 2 milliansky to 8 milliansky across 1 or 2 years. And it is also highly circularly polarized with fractional polarization about 20%. Here is the radial cutout, and you can see the whole field in the Stokes I, they have lots of emission, but in Stokes V, they are quite clean because not so many sources can generate Stokes V emission. Usually flaring stars or pulsars can have Stokes V emission about like 10%, 20%, or like 50, 100%, but they AGN usually only like less a few percent. So our source is quite unusual in this aspect. It also detecting the Stokes V. And another property is we didn't find any optical, infrared, or high energy counterpart of this one. So here is the near infrared overlay. And this is our target. The white circle is the 5 sigma position uncertainty. There's no infrared counterparts near like near it in the VLMC and recent Gemini catalog. And we also have compact array to do follow-up observation. We found the spectral index is quite steep. It's varying about -3 to -1, which is very interesting. So some possibilities related to it. As I mentioned before, like not so many sources have Stokes-Wave emission. Brown dwarf is one of it. And here is a radio to near infrared emission versus a fractional polarized emission of the for the whole known radio emitting stars, and our sources like higher than our known radio emitting stars. This is quite unusual, like indicated some extreme magnetic activities if it is a radio emission stellar object. And another possibility it also could be a pulsar. Pulsar can also show circular polarization, but we didn't find any positions. But it still could be a pulsar, like highly scattered or some other possibility. So magnetite can also be variable and can also have polarized emission. However, we obtained a swift X-ray observation, although we didn't find any detection, but the upper limit didn't rule out a possibility of magnetite. So it could also be a new class. That is the most exciting one. So this is not the only one people found with steep spectrum, but no positions. So if it is like a member of a new class, that would be very exciting. Thanks.
Hello, everyone. Thanks so much for the organizers to allow me to give a poster of my study for this conference. My name is Ziqian Wang. You can call me promoter. I'm a second-year PhD student in University of Sydney. Thanks for my supervisors. Today, I will give a brief introduction about my study, which is reliable stellar abundances of individual stars with the MUSE integral field spectrograph. So, as we all know, galactic archaeology is at present being propelled by a number of completed or ongoing large-scale spectroscopic surveys like GALA, Apogee, and LAMOST. These multi-object spectroscopic surveys combined with data-driven models make it possible for us to obtain precise and accurate stellar labels for millions of stars. However, one issue on all these surveys is that traditional multi-object fiber spectrograph cannot do dense fields, in particular the bulge and the clusters, because the fibers cannot be placed too close to each other on the sky, making the observations of clusters and the bulge very difficult. Therefore, we need a new instrument which can help to extract the stellar spectra from dense fields. Finally, we find MUSE, which is traditionally used to study galaxies, can be used to overcome this problem. It is a second generation integral field spectrograph that is installed for the VLT of ESO. Since the first slide, most of the objects MUSE focused on galaxies, like the left image, mainly helping scientists to research on their properties. However, some research groups are using MUSE to observe some dense fields with full of stars, just to see the right image. Most of them studied the radial velocity, temperature log G, metallicity, and some exotic spectra. However, until now, there is not a good way to derive stellar labels of stars in such a dense field. For LAMOST spectra, which is the combination of DDPen, which is a well-trained narrow network model, we can derive more than 20 stellar labels, which is with the similar properties of LAMOST and MUSE. What if we apply DDPen on MUSE spectra? Well, the answer is yes, for some of the elements. Here, I just showed the flowchart of our method. First, we use PempoMUSE to extract the stellar spectra from MUSE data cubes. And then we use the line spread function to degrade the spectra from 3000 to 1800, which then can can be applied on data-driven pen to derive the stellar labels. And after precision check, we can get our results. To verify our method, we compare the stellar labels using our sample with those from Lamont samples. You can see the difference is really close to 0 for these parameters, which proves the ability of our method. We also select some dense fields and estimate their stellar labels. Not only we can do this, other services, including Lamont, cannot do that. And we compare the stellar parameters using our sample with those from previous studies, which shows good consistency. Now, this is another comparison using our method, and you can see the trend is really similar as well. So here is my take-home information, and I will stop here. Thank you very much.